Well, welcome back, guys, and I do hope, as ever, during this challenging time, you and your family are keeping well. So what we're going to look at in this video is we're going to look at Coulombs Law, and that will allow us to calculate the force between 2 point charges at different separations. Okay, so now let's look at this a little bit more mathematically, and we're going to look at Coulombs Law. And as you might guess, hinting at gravitational fields, it's a little bit like Newton's law of gravitation, but it's for forces between charges. Okay, so what I'd like you to imagine is a positive charge here. There it is. And we'll give that charge the amount Q, okay, the quantity of charge. And we'll put another object over here that's negatively charged, minus. Okay. Now, I get a bit annoyed with the textbook on this. I would like to call this Q1, and I would like to call the charge on here Q2. The textbook we have gives that charge little q. Okay. Let me tell you why I don't like that. Okay. Typically in physics, we use large Q for a large quantity of charge and small q for a very small quantity of charge, a few electrons or a few protons. Okay, but you're going to have to go with it that q is the charge on this object, and if we've got another object, we're just going to use lowercase q. I think they do it to avoid all the subscripts going Q1, Q2. Do you remember big M, little m? Sort of made sense with the gravitational field work we did because it was the Earth and the apple. But, if it's two stars, then big M and the other one is a big M as well. So I like M1, M2. Anyway, I'm probably going to keep going on about that. But can you get it in your head for now that both of those Qs just represent quantities of charge, and we use two different cases of Q because we want to separate the two. We want to know which object we're talking about. Okay. Now there's going to be a force between these. Okay. So the Q here is going to be pulled that way with a force, okay, of attraction, and this one is going to feel an equal and opposite force. And we have to be careful here to say, well, okay, if that one's positive, then that one's negative. Okay, so we've got the direction of the force vector, and you'll also notice that between the centres of these two, so we're going to imagine that they're point charges, there is a distance radially outwards, so let's call that R. Not S for displacement and not D for distance. We're going to call it R. Okay. Now, if we draw that in a slightly different way, imagine we've got two positive objects. So here's one and here's the other one. Okay. And instead of attracting, they will repel. So on this one, we've got a force that way, and on this one, a force that way, and the forces are equal and opposite. And we defined to the right as being positive, so that has a force F on it, and that has a force minus F. Okay, I better just put the charges on these. So we said that we got charge Q. Now, I have no idea how large that Q is, because I haven't given you numbers. And rather interestingly, I've no idea how big this Q is either. Okay, so I want to make a very clear point here that that could have more charge than that one. Okay, but the forces, Newton's third law, the forces between them will be equal and opposite. Okay. I could go on here about what would happen if these were solid spheres. Okay, well, I will do very quickly. If one sphere is heavier than the other, has more mass, then it will move away with a lower F equals ma, a lower acceleration. But I'll just say it again. Okay, these two, it doesn't matter what the charges are. They can be different amounts of charge. Okay, but the force on big Q of little q will always be the same as the force of big Q on little q. Have I got that the wrong way around? And the force of little q will be on big Q will be the same. Did I explain that well? Okay, the left one on the right one will be the same force as the right one on the left one. If you spend a little bit of time thinking about that, okay, you'll get it. Let me see if I can do it without getting in a real tangle. If this is a big charge, and that's a little charge, okay, this big charge won't push on that one much because it's a little charge, okay. But if this is a little charge and that's a big charge, this little charge is not capable of pushing on that one very hard. So I hope I've justified why the forces are equal and opposite. Okay, it would be a nice exam question. I'll make the numbers really huge. 10 coulombs and 3 coulombs. Draw force vectors on them. Okay, and I bet you some people would have a bigger force vector on one side than the other. No, done enough of this. They are equal and opposite. Okay, let's get back to Coulombs law. So we remember that these two, shall we make them point charges now? So from the middle of them, they're separated by a distance that we're going to designate r. Okay, so now we're up and running. Let's have a look at what the force depends upon. Well, I think you'd be pretty clear in your mind that if the charges, either of them, are larger, the force will be bigger. So the force is proportional to both the charges multiplied together, so the product of the charges. Okay. Now I will just go off on one for a moment. This could be Q1, Q2. Yeah. Or it could be Q1 and Q2, or it could be E and E, if that sort of makes sense. Okay, so very quickly, this was my rant about the charge on the first one, charge on the second one, usually quite large quantities of charge, much more than the charge on a proton. Okay, or it could be a small charge and a small charge. It could, of course, be big Q and little q. Or it could be the charge on, now this is a fundamental charge, remember, not the charge on an electron, that's minus E, charge on the proton and the charge on another proton. You can use lots of different letters, okay? So in other words, you could say this is, Q, which we've got here, or finally, you could say Q1, Q2, okay? Rant over, but just understand that Q's represent charges, and physicists often like to use a little q when there's a little charge on an object. So, Coulomb said the force between 2 point charges, is proportional to the product of their charges, and I think you can guess it, and it's why I put the R in here. Okay, the force between them is inversely proportional to their separation squared. Okay, now do you remember the square comes in here partly because the field spreads out in that direction, but it also spreads out in the direction towards us as well. So there's a sort of spreading in that direction and that direction, which gets the fact that as we back off a distance, so if we double the distance, okay, we make the field sort of twice as spread out in that direction, twice as spread out in that direction, so 4 times less field lines per meter squared. So let's put all this together and we'll get our equation for this. So therefore, I don't know if you can see the green pen, therefore we need to sort of put all this together in an equation, and you will see that the force between point charges is proportional to, well, the 2 charges multiplied together, so the product of the 2 charges, okay, and inversely proportional to their separation squared, okay. And now it gets a little bit complicated. How do we make this into an equation? Well, of course, what we do is we say that F is equal to Q1, Q2 upon r squared, and we put a k in here. Some kind of a constant, okay? Now, again, I don't want to go into detail for a long time, but this is coulombs squared per metre squared, and that's newtons. Okay, that's newtons. So this here, if you were to work it out, and it would make a good A-level question, okay, is not a dimensionless constant. This constant in here has to have some units, okay? And it's a bit of a nightmare, okay? You will get used to this, okay? The constant has a number in it that relates to the geometry of space, shall we say, to keep it easy, okay? So k, I'm going to put it over here. The constant, you'll get very used to it, is 1 over 4 pi, okay? And at university, I don't think at A-level, at university you would expect to derive this to see where that 4 pi has come from, okay? And then this interesting thing. Oh, 1 over 4 pi has no units, of course. Epsilon naught, okay? So, come back to epsilon naught in a minute, okay? That is a number, and that has units, okay? They give you epsilon naught in the exam, so you need to work out 1 over 4 pi epsilon naught. It's a bit nasty of them, isn't it? Most physicists know 1 over 4 pi epsilon naught off by heart, but they give you epsilon naught on the formula sheet, if I remember rightly, so you need to work out 1 over 4 pi epsilon naught, and that is the k there. Okay, do you remember big G, the gravitational constant? This is the equivalent for electric fields, okay? And interestingly enough, we expect electric fields to be very strong, okay? So this is below the divide and is a very small number. So epsilon naught, yeah. Well, not all physicists, but people like me confuse its name. It's the ability kind of for electric fields to go through a vacuum. How well electric fields are permitted to travel through a vacuum. So this is the permittivity of a vacuum, yeah, so of free space. Hope I spelt permittivity correctly, okay? And it has this value. Okay, you don't remember this, but you get used to it. 8.85 times 10 to the minus 12. Okay, and again, you could do a little bit of work on here to find out what units this must have. Electric fields, capacitors, farads per meter. Okay, so I'm kind of running out of space on the page here, but this is Coulombs law, but the formula for the force between two charges, and remember the direction of the force, yeah, if you need a minus in there or not, okay, so should we do the magnitude? The magnitude of the force will be 1 over 4 pi epsilon naught QQ over r squared, okay, and you're bound to get some questions where you do that in the A-level. So, Coulombs law and the force between 2 point charges. It's important you understand they're point charges. Yep. Our formula was F is equal to 1 over 4 pi epsilon naught. I'll separate that constant out. Q1, Q2 upon r squared. Okay. When you do this in exams, for heaven's sake, sort of, do it a bit at a time and work it out a bit at a time. Don't put it all into your calculator because you'll mess it up. I do. And then I forget the squaring of the r there, all those sorts of things. Okay. So how would you test this? Yeah, what practical could you do to check this out? So let's look at a practical test of Coulombs law. So, just to remind you, of course, that is not Coulombs law, Okay, that's the formula we use. Remember, Coulombs Law talks about the relationship between force, charge, and separation. Okay, so a practical test. Well, this is quite interesting. This is going to stretch my drawing skills to the absolute limits. Okay, you have to imagine hanging from the roof, or more importantly, on a stand, an insulated stand. Okay, so there's the roof. We're going to place a charged conductor. It's the usual story. So this is an insulating support. Back in the day it was silk, and we're going to put a metal sphere here. Okay, and we'll charge that metal sphere up in a minute. Okay, so what we'll do next is we'll get a balance, a laboratory balance. So I'll draw that down here. So there's the top pan of the balance. And here's the sort of structure of it. Don't you wish I'd drawn this earlier? Okay. And we're going to put on that balance. So we have it calibrated in grams, which we then can work out what the weight is in newtons. I'll just put a number on here just for the hell of it, 0.01 gram. Okay, I'm just making that up. And then put onto that balance another insulated rod, and on the top of that insulated rod another metal sphere. Okay. Now, the crucial thing is that these two are uncharged, okay, and we then zero the balance. But what you'll notice is that their centres are separated by a distance r. There we go. Now, I'm not going to do this experiment in any great detail, but if we zero the balance, okay, we now realise there's no force between these at all. So the next thing we've got to do is we've got to charge them up, okay, and see what force we get between them, and then we can change the separation and we can change the charge and investigate Coulombs Law. So here we go. Yep. Set this up. Okay. Touch this on a high voltage power supply, maybe the positive terminal, and touch that on the same positive terminal of the power supply. So you'll rip electrons off this one, you'll rip electrons off that one, and they'll both become positively charged. Okay. And what you'll notice is that they will have a field between them that will be repulsive, sort of field lines coming out and doing this sort of thing. Have I got that right? Yeah, the way a positive charge would move. Okay. And we can do a couple of things here. Okay. What we can do is we can move this one closer, move the top one closer and closer, reduce the R, okay, and see what happens to the force. Okay. And of course, you'll notice that the force will vary with 1 over r squared. So as we get closer and closer and closer, the force will grow very quickly. Okay, so that looks at this part of the relationship. I'm not going to go into the detail of what numbers you would take, okay, and then you'd plot graphs, and then what would you put a force and 1 over r squared on the axis to get a straight line, etc. Okay, you know that sort of stuff. And then how would you check out the QQ bit? Okay, well, what you could do, you could use a Coulomb meter, but that doesn't work very well, is you could touch this to 1,000 volts and 1,000 volts, okay, and argue that there's charge on both of those. And then repeat the experiment for a fixed R with 2,000 volts and 2,000, 3,000, 3,000. Do you see what I mean? Okay, so what you're then doing is seeing how the reading on the balance changes with respect to the charges on the objects. I think some schools, or at least back in the day, some schools really did this. You needed a really sensitive balance, so we could do it here. Okay, but it tends to work out reasonably well. You need to get quite close with these, and you need a high voltage power supply. Okay, but it does show quite nicely when you collect the data that Coulombs law does hold pretty well, even for these which aren't exactly point charges but can be treated like point charges, that the force is proportional to 1 over their separation squared, and the force between them is proportional to the product of their charges. So now let's do a quick example. And the example I'd like to do is between 2 protons in a helium nucleus. Now, I'm looking only here at the electrostatic forces between them, the Coulomb forces, okay, not other forces that might be holding them together. And we can forget the neutrons because they're uncharged. So our example, take me a while to just do this, we'll be using the formula that we've just worked on. So you can follow me through with this, or pause the video if you so wish. So let's calculate the force between the 2 protons in a helium nucleus. Okay, so you remember that helium has 4 particles in the nucleus, but 2 of them don't play any part because they're neutrons. It's those 2 protons we're interested in. Okay, so this is a fairly typical sort of thing to do once you've got the idea of Coulombs law. So here's our first point charge, we consider our proton, and here's our other proton. So we need an idea of what charge is on those protons. Okay, I think you know that. And we also need to kind of know how far apart they are. Okay, so if you take the width of a proton and slide halfway along, you're now at the middle of the next one. Okay, so these centers, yep, are separated by a distance r. There we go. And it's pretty much the diameter of a proton. So should we make r equal to 1 times 10 to the minus 15 meters? Okay. So what do we know about the charge on a proton? Okay, well, I'll just try to not do it in the same red, okay? That proton there, we know it's a proton. The charge on it will be E, the fundamental charge, and that is positive 1.6 times 10 to the minus 19 coulombs. Okay, good that we get all of our units right. So, over to you guys. Why don't you just pause the video now and see if you can work out what the force between those 2 will be. And just before you run off and grab your calculator, it seems inexplicable that a helium nucleus stays together, because those 2 are positive and will repel. Okay, so I wonder how the nucleus actually stays together. But you're going to work out the Coulomb repulsion between those 2 protons, which are touching each other in the helium nucleus. Good luck, and I'll see you in a few minutes. Good, so how did you get on? Let's work through it together. So we know that the formula we need to use, is F, the force between them, will be equal to 1 over 4 pi epsilon naught QQ upon R squared. Okay, now it's at this stage we get numbers all over the page, so I'll try my best. Okay, we've got to work out 1 over 4 pi epsilon naught at A level, so the force will be equal to 1 I'm going to need a ruler for this one. So 4 pi, yep, and then epsilon naught, 8.85 times 10 to the minus 12. Okay, farads per metre. And then the Q upon R squared, so that lot times by, now here's the clever bit, okay, 1.6 times 10 to the minus 19 times 1.6 times 10 to the minus 19. So squared, it's kind of an easy one, that, divided by their separation squared, that's the bit I often forget, 1 times 10 to the minus 15 metres squared. Okay, now if you're my age and you're watching this video, you probably won't be, but if you are, you'll know what I mean by this. When we had calculators, our calculators back in the day, and the one you've seen me use in class, can't store lots and lots of numbers on the screen. And actually, I think we got maths more often, we got it correct, because we would work out that first and then reciprocal it and store that away somewhere. We'd then work out that and store it away. We'd work out this and store it away, and then we divide them and multiply. Okay, we didn't do it all in one great big chunk on the screen. Now it's over to you on this, but I would be really careful about doing it all in one go. In fact, it's a good idea to lay your working out on the page, but keep the numbers in your calculator so you don't accumulate rounding errors. You do the rounding right at the end. Okay, well, the joke's on me if after saying that I got this wrong, okay, but I get 240 newtons. Now, 240 newtons, okay. You know how cross I get with A-level students who are quite happy to write down ridiculously stupid numbers and not realise they're stupid. Like calculate the mass of a proton, 1 times 10 to the 28 kilograms or something, and you're thinking, where did you get that number from? Okay, that is phenomenally large. Okay, that is an incredibly large number. But I think I've got the maths right. Okay, and I will just remind you that if we put that into F equals ma, okay, if we put this force between these two into F equals ma and work out F over m, in other words, the acceleration of one of these particles, it will be a phenomenally large number. Okay, it's correct, but helium nuclei do not fall apart. And the reason for that is quite complicated, and when you do some nuclear physics you'll find out something about how the masses of these change when they're in a nucleus. We have something called binding energy, but that's probably for another time. Okay, but the point I want to make is there must be something gluing these together. There must be a different field that we don't really do at A-level. Okay, we just mention it, called the strong nuclear interaction or the strong nuclear force. So I'm just going to write here strong nuclear force, because this would be a good example of do a calculation to account for the fact there are very strong attractive forces in the nucleus holding it together. And the strong nuclear force is felt by neutrons as well. So the neutrons in here play a part. Okay, they do not play a part with the Coulomb repulsion. Finally, if you just forget the strong nuclear force, I've got ahead of myself. Okay, how strong would the gravitational field have to be between these two? How strong would the gravitational force have to be between these two? Okay, to bring them and to hold them together? Well, it would need to be an equal and opposite force. And if you use Newton's law of gravitation for the mass of two protons, why not do it in a minute, separated by this distance, you'll find the gravitational force is many, 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 many orders of magnitude too weak. So we've shown that, or you could show that, the gravitational force is not what holds protons together in a nucleus against the Coulomb repulsion. So we need to invoke a new idea, the strong nuclear force. So I do hope you found that look at Coulombs Law really useful and you understand it well. I'll be making another video soon and I look forward to seeing you then.